Hello, everyone. Welcome to another episode of the Engineering Student Experience Podcast. I'm Paul Nissenson from the Mechanical Engineering Department at Cal Poly Pomona. In today's episode, we're going to cover the field of aerospace engineering. Recently, I sat down with Dr. Don Edberg and Dr. Todd Coburn, who are faculty members in the Aerospace Engineering Department at my university. We discussed what aerospace engineering is all about, including the subdisciplines within aerospace engineering, the career paths available to aerospace engineers, the types of courses taken by aerospace engineering students, and various tips for aerospace engineering students to succeed in college. Don and Todd have each dedicated their professional lives to working as engineers in the aerospace industry and to teaching aerospace engineering courses. I believe anyone who's interested in entering this field can learn a lot from their words of wisdom. I hope you enjoy this conversation. All right, well, I'm here with Don Edberg and Todd Coburn, both aerospace engineering professors here at Cal Poly Pomona, and today we're talking all about aerospace engineering. Don and Todd, thank you so much for taking time out of your busy day to have this conversation.
We're happy to be here.
So let's give our listeners a little bit of idea of who you are. So where did you go to school? What kind of research did you do? What were your interests back then, and maybe some of your current interests as well? I know you both have extensive experience with industry. I'd love to hear about that. And how long have you been here at Cal Poly Pomona, and what are some of the courses that you teach here? And maybe Don could go first.
Well, let's see. I have an undergrad from UC San Diego, and my graduate and PhD degrees are from Stanford. And I have been afflicted by the airplane bug since I can remember. So I didn't have much of a problem making a career decision what to study. But I've been working since 1985, worked at JPL, General Dynamics, McDonnell Douglas, AeroVironment, a lot of companies that don't exist anymore or got merged with other companies. Did I say JPL?
Yep.
And McDonnell Douglas and Boeing before I started teaching. And I actually started on, my first day was 9/11, which was a very interesting day. But after that, I've been here now 18 years, and I've enjoyed every minute of it. And I currently teach the senior vehicle design sequence here at Cal Poly, where the students design either aircraft or spacecraft or launch vehicles. And it's a year-long course. We call it a capstone course because it's one of our fundamental courses in the department as far as being accredited and graduating and things like that.
How about you, Todd?
So a lot of folks in aerospace are drawn because, as a child, like Don and many others that come to engineering. I was a little different story. I was going to be an actor. And then when I realized I weren't making Westerns anymore, I decided I'd be a lawyer or veterinarian. But I took a test as an 11th grader, and it asked, "Are you good at math?" I said, "Yes." How much money do you want to make? I said $60,000, which is a lot of money at that time. Do you want to work with people? No. And it said engineer. And that's how I became an engineer. So I said, okay, I'll do engineering. I had no idea what it was. It's actually been a pretty good fit for me. I started out the junior college because I was working 20 hours or more a week all the way through. I had a place to live and food to eat and my folks. Everything else I paid for myself. Went to the junior college 2 years, went to the Long Beach State, Cal State Long Beach, for a couple more years, got my bachelor's. Just as I was finishing, I realized, wow, I'm just beginning to figure this out. I can't stop now. I'd already been working as an intern at Boeing, which was McDonnell Douglas at that time, since '87, shortly after you. And so I went ahead and took a full-time job, making a lot better money, and then continued on part-time. I actually got married my last year of college. We got pregnant about 6 months later. So because I now had a new family and a young child, I slowed down and I took basically one class a semester until I finished, plus my thesis. After that, my wife was kind of tired of me being in college, so I just hunkered down with my bachelor's and my master's in mechanical engineering to work. Worked in aerospace structures my whole career pretty much. Started out in mass properties, switched to structural analysis shortly after that before I graduated, and then continued on for 9 years. After 9 years, that was getting too easy. They had some changes at the plant. I ended up doing rocket analysis. My first 9 years in aircraft metallic structures, my next 9 in rocket composite structures is completely different. I started as the lead, which was a big struggle. But it was fun. I did that for about 9 years. When that got too easy, I went to the scramjet for a short time. That got pretty easy fast because it was a small little piece of information. Then I went back to manage the group I'd started at for 7 years. When that got too easy, I was looking for either a director of engineering or a teaching job. I didn't think I was going to take teaching because of the difference in money, like half the pay. But I got an opportunity to come to Cal Poly in either mechanical or aerospace, so I took it. What the heck, money's not that important to me. I found, sure, teaching is half the pay, but it's actually also twice the work, which I didn't expect. But I do enjoy it. Actually enjoyed everything I've done.
But it's also twice the fun.
I don't know. I've enjoyed it. I have enjoyed everything. Yeah, I actually got I had my bachelor's and master's early in my career. Later, I came back. 12 years later, I went back for a PhD. I'd been doing consulting for a number of years on the side. I thought a PhD. I was thinking about going to seminary or law school or a PhD. I decided, well, I don't need seminary to study scripture, and I don't law school. I'm going to start over. PhD might help move forward with the skills I'm already kind of at the top of the crest for, and open up more opportunities for teaching and for higher advancement in industry. So and for research money, because we're doing research with some of my clients. So that actually laid the groundwork. I don't think I would have had the same opportunity in education if I hadn't gone back for that PhD. Yeah. On the way to the PhD, I got a master's in mathematics. So now I have a bachelor's and master's in mechanical engineering, a master's in mathematics, and a PhD in engineering and applied industrial mathematics.
Wow. I think you should have stuck with acting.
Probably.
Yeah.
Probably should. My students get a piece of that in my classes.
Now, you mentioned early on that you didn't really know anything about engineering, and actually that's what this is kind of what this whole podcast is about, is to help give high school students a better idea of what engineering is all about. So that's great. So if you were actually talking to a high school student and you could just describe in a few sentences what aerospace engineering is, what would you tell that high school student?
Well, obviously, I would say aerospace engineering is dealing with vehicles that fly in the air and space, things like that. But we also deal with other vehicles like cars, aerodynamics and engineering, submarines, wind turbines, windmills. Anything basically that goes through the air or through the water is subject to aerospace engineering rules and applications. So we have a lot of folks that are not working on airplanes or rockets. And it's still pretty interesting stuff.
How about you, Todd?
So certainly there are folks that are attracted to aerospace engineering because they like looking at things that fly. But for students that aren't really sure what they already want to do, I would first have them think about engineering versus other opportunities. Engineering is, so if you're pretty good at math, there are people that like math, trig, calculus, and there are people that don't. But the question is not really whether you like them, it's whether you're good at them naturally. If you tend to be good at those classes, you tend to be a linear thinking and you're fairly creative, then engineering is probably a good platform for you. And then it's a matter of figuring out which of the engineering disciplines is a better fit. I would choose a more broad one like a civil or a mechanical unless you're really attracted to things that fly or things that fly through the air. Missiles and aircraft and rockets and satellites, if that fires your imagination, aerospace is the place for you. If that is of some interest but not main interest, actually a broader engineering background would probably be a better fit.
Okay. I would take issue with that because an aerospace degree includes many different disciplines like propulsion thermodynamics, like structures, like controls, a whole bunch of different outlooks, and many of our graduates end up not in aerospace engineering just because they have a broad background and are able to apply themselves using the principles of engineering, which are pretty universal to solving other problems.
Sure.
So I would say that if you're not sure aerospace is good, just because you can go out in many, many different directions as a result of the vast number of subjects that we try and teach here. Yeah, for example, a structure is a structure. So an aerospace structure has certain principles. So does a building. So does laying down a highway. And the principles we teach in our classes are applicable to all the different disciplines.
And that's really a good point. I mean, that's actually true in all the engineerings.
Right.
So if you look at aerospace structures, there's probably a higher percentage of mechanicals and civils in aerospace structures than aerospace engineers. I think there's a couple reasons for that. One of them, folks that are interested in aerospace generally end up more in avionics or in controls or loads, where they get a higher concentration of those courses as they pertain to aircraft. And folks and a lot of times, a lot of aerospace programs don't do as strong of a job in structures as they could. We've actually corrected that here at Cal Poly, and I believe they're getting a better foundation in structures than perhaps anywhere in the world because of the practical way these courses have been designed for our students. It's very practical, it's very usable. And but as you were saying, it's true that our students can go elsewhere, and it's also true that mechanicals and even civils can come, and there are a number of them in aerospace. So it kind of goes both ways.
Very true.
And it's true you're not completely limited, but some degrees, if it has a specific name, it's going to tend to be more limiting than one with a broader name. That's kind of the point I was making.
So you've already mentioned a lot of the subdisciplines within aerospace engineering. So you were mentioning that there's structures and controls and rocket propulsion. And if you could list all the different possible subdisciplines, and then I think you've also mentioned some of the courses that you might take, but if we could maybe explicitly spell that out so anyone listening might have a good idea of what are all the different paths available to them.
Well, let's see. There would be aerodynamics, fluid dynamics, fluid flow types of courses. There would be structures, structural dynamics, vibrations, that sort of thing. There would be propulsion, thermodynamics, and that related subject, flight mechanics, stability and control, orbit, space sciences, things like that. Management, we have several courses in project management, which are very important in terms of getting things done in reality. Can't think of any else at the moment.
Excellent. Loads, one subdiscipline within structures is fatigue and damage tolerance.
Yes.
Often that's broken out into another group because it's kind of specific and requires special study.
Some statistics associated with that, probability. Lots of mathematics, but it's all applied mathematics. It's not basic mathematics. So you do need to have a good mathematics background and some skill at it. But,
and kind of piggybacking on that, a lot of folks, they'll get into math, they'll find they're good at it. Then they'll get into trig, they'll start to dislike it. They'll get into calculus, they'll start off enjoying it, and then they'll begin to hate it as they go into some of the detailed calculations with no apparent applications. Mm-hmm. But if they bear through it, they will find as they go higher, it doesn't get more complicated, it gets more applied. And they will start seeing applications that actually make sense, where they'll see the applied calculus starts allowing them to do things that can't otherwise be done. It's very fun.
Yeah, I remember I took a class in engineering mathematics, and one of the things we learned was solving Legendre's equation, and it turned out to be the equation that dictated the orbital mechanics for atoms, for atomic levels and energy levels and that sort of thing. It was really exciting to see an actual application pop out of a bunch of theoretical equations. And that engineering is like that. Yes. All the mathematics leads to something that you can either visualize or see, and that's much better than just solving equations.
Another mistake that students often make when they're choosing their career is they'll sit there, and I was kind of one of these also, and they'll say, I don't want to sit behind a desk. I don't want a desk job. And these same students will go sit down at a computer and play World of Warcraft with 15 hours straight without eating or drinking. If you can do that, you are a great fit for engineering, because I'll go to work and I will start working, and the next thing I know, it's time to go home. My day flies by because my mind is active. It's not like I'm sitting behind a desk. Although sitting at the gym will have a nice perspective on the roundness of your muscles and the shape of your form, if you stick with engineering and stay in an analytical subdiscipline of that, your mind will be gorgeous. If somebody could see it, they'd slip the ring on your finger just like that.
So what, for students who get a degree, a bachelor's degree, let's say, in aerospace engineering, what are all the different types of career paths that might be available to them in both private industry and in government? And what are some of the new emerging fields right now that are like really interesting and really hot in aerospace engineering?
I would answer the second question first.
Sure.
The new and emerging fields I think that everyone is aware of right now are so-called drones, which we don't like that name. We would prefer to call them UAVs, uninhabited aerial vehicles. And that field is literally exploding with companies wanting to deliver packages with it, with medical supplies being delivered to remote locations, emergency rescues, and personal transportation is about to pop out of that. We're about to see where you can strap on your personal UAV and fly somewhere and land if someone can figure out how to control all the traffic and make sure it's safe. But I think it's going to be really exciting in the next few years. We also have a lot of development going on in high-speed vehicles. I'm sure you've heard of the stuff that SpaceX is doing with their Starship and talking about point-to-point transportation around the world. I don't know if that will ever come to pass, but it's still an outgrowth of aerospace engineering that is still open to be developed. And I think the jobs and the careers and the problems that will be solved are going to continue to be growing and interesting. And I'm only sad that I can't work on them after I retire very much. Maybe as a consultant I can stay in touch with that stuff, but lots of exciting things. That's the beauty of aerospace engineering, is it's such a quickly changing field that you have to stay abreast of what's going on, because there are so many developments. You need to pay attention and keep up your knowledge and learning level so that you can stay current with all these things.
So that nails emerging markets really well. There's actually a lot of jobs, and has been for a long time, in commercial aircraft.
Yes.
You've got major companies like Boeing and Northrop and Airbus who are hiring a lot of engineers. You've also got, fortunately, led by Elon Musk and SpaceX, there's now a number of brand new rocket startup companies. You got Virgin Orbit, you got Blue Origin, and others popping up all over the place. Where a lot of industry was leaving Southern California, now we've got a lot of folks that are setting up home here because there's so many engineers available. So there's actually a lot of opportunity, both in emerging fields and in repeated
steady
engineering
fields. Yeah.
And around these large companies, there are a lot of little mom and pop shops doing aircraft repairs and modifications and alterations.
Parts suppliers, manufacturers.
Yeah. So there's actually a lot of opportunity for engineering.
What about in government? What types of jobs related to aerospace engineering are in government?
We work a lot with the government labs around here, such as JPL, such as Edwards Air Force Base, Air Force Research Lab, the other NASA centers we have relationships with. So there's quite a bit of work there. DoD in general is probably the biggest customer of aerospace engineering in terms of vehicles and services. Because they buy airplanes and they buy launch services, and they do a lot of sponsored research and development, which is what I spent my first part of my career working on. I tell my students that they're probably going to be working for the government at some point during their careers, and it might be a good place to move to after you've stabilized and have a family, and you don't want to worry about layoffs and things like that, to find a government job, which might not pay as much, but it's much more steady and reliable in terms of a commercial company compared to a commercial company.
I've enjoyed my government job here. So
Yeah. Well, many of us switched to teaching just for that reason, right? Go ahead.
Certainly a number of government jobs. There's actually, the government has worked really hard. They work closely with industry. So there's actually a lot of jobs that you will do for the government through industry. So if you work for Boeing or Airbus, or, well, maybe not Airbus, but Northrop or a lot of these companies, they're going to be going after government funding for various projects. You can either work commercial or work a government-funded job. A lot of times you won't even know you're really working for the government directly in the way your job works out. There's also a lot of research money that's intended for dual use, both commercial and military applications.
And many of us worked on both sides. We did some R&D for the government. We did some commercial stuff for the company by itself. So it just depends on where you end up. And it changes daily. So that's one of the nice things.
Within the subdiscipline of aerospace engineering, one of those is that broad realm of aerospace structures that we mentioned. And one of the beauties of aerospace structures, not only is it super fun and kind of like an endless career of learning, but it actually is probably the biggest employer of jobs of any of the other subdisciplines of aerospace. There are a lot of jobs in aerospace structures, both within aerospace and in other applications. If you get good at structures, you can do a lot of things. And this really applies to mechanicals and civils also, where requires a huge pool of engineers that understand how to analyze those structures for static loads, for fatigue loads, and even for damage tolerance, where we're actually analyzing how cracks grow through the structure. That's really important for repeated use structures like aircraft, ships, and things like that.
Or more importantly, how to stop the cracks from growing through the structure.
Exactly. That's true. Or analyze how quickly they grow. Because a lot of times we allow them to grow as long as they withstand the life of the aircraft.
So so far we've been talking a lot of stuff we've been talking about has kind of been a little more general. What I think might be interesting for the listener would be taking a more concrete example. So let's say that let's stick with Boeing. Let's say Boeing wants to make a change to one of their aircraft designs, or wants to even maybe develop a new aircraft, which could take quite a long time. How would aerospace engineers be involved in all facets of that process, and how would they be interacting with other kinds of engineers during that process?
Well, starting out a new product usually begins with a set of requirements. So some group of engineers or technicians or whatever would meet with a potential customer and try and figure out what the customer needs. Excuse me. Then once we have a set of needs available, they would sit down and figure out what we call the design drivers. What's the most important part of that set of requirements that needs to be satisfied? And then basically size the airplane around that set of requirements. And that involves a very interdisciplinary group of structures people, of aero people, propulsion people, stability and control. So it would be a very small team, but all the different disciplines would be represented. And they would go through some sort of a design process that would outline what this vehicle would look like, see if it would work or not analytically, and then go back to the customer and see if that's what the customer really wants. And it would be this iteration process where the design would be improved several times. And once the customer would commit to saying that they wanted it and there was a definite need for it, then the design company would go find financing or use their own money to begin an applied design and development program, which would eventually, after many years and many millions of dollars, would lead to a new airplane or a new rocket.
Sure. And then different kinds of projects require different levels of attention to those details. So if we were designing, let's say, a brand new plane, like a 797 or something, they're usually going to start off with a small group of highly experienced engineers. They usually call them advanced design.
Yeah.
And these folks have good broad knowledge, often not quite as deep in all the subdisciplines, but good broad knowledge. And they will do most of the primary design, wingspans and basic shapes, and how long the fuselage is, and how many passengers, and does it do freighter and passengers or what. Once they have developed that, maybe for 6 months or a year or maybe more, they will then start growing the group and having different teams that will go and flesh out the design and the electrical and the structures and these kind of things and the loads. And your group will get larger and larger and larger as you get closer to finishing. And it gets harder and harder to keep moving forward. This is why the 787 was so late, is folks, they had a lot of younger engineers with younger managers, leaving all the experienced people, or a lot of them on other programs, starting off with a younger crowd. They end up overusing tools, overanalyzing most of the things, not focusing on the right things, and then ending up being late and needing a lot of help to get that completed. If you work for a smaller company, like one of my clients down here in Fullerton, they got a little job to modify a BAE 146 aircraft to make it a firefighter. They were told they needed 5,000 gallons of a fire retardant. They needed to drop it in a certain number of seconds. So they came up with a cylindrical tank design that sits up on the floor. When you do that kind of analysis, it's you don't have nearly as much information as you do at a big, large manufacturer, and you have to use pieces of information that are available on the public domain, like weight and balance manuals and things, to go and post-analyze the structure for the loads and the critical loads, and then analyze only the pieces of structure that are affected by those changes, and getting the electrical systems and those kind of analyses done, and then showing that your weight in CG is not compromised, or if it is, what are the flight characteristics for that? How much testing is required to follow that up? So it's actually really fun, and it's really easy to overcomplicate, which can mean you won't finish within your design. You have to have people that are knowledgeable and know how to keep it simple in order to keep on task and complete on target. So there's actually a lot of opportunity, and then there's a lot of repairs and things like that are available.
Yeah, one of the mottos that I try and teach my students is that better is the enemy of good enough.
Right.
You need to learn to know when to stop and go ahead with what you got instead of trying to make it better, because you can always make it better. But at some point it will do the job and you get the job done, and that's the time you quit.
Yeah, and along those lines, when you get the mindset of being, I call it a state of perpetually being done. What you want is a simple design that will work. And then you look and you see if you have more time, and if you do, you make it better. And then you make it better and you make it better. This way you don't come charging up trying to do something that's more complicated than it needs to be and doesn't meet all the requirements, and then you can't finish. So it's a challenge to keep it simple enough to get done, and then you can evaluate, you have time to make your answer better. It's a good engineering skill that actually applies across all the disciplines.
So we have folks that are what I would call a big picture type of person, where they understand all the parts of the problem that they're associated with and some of the other parts, so they're able to interact with other disciplines and other workers.
And these would be people who've been in the industry for a while?
Generally, they have experience. And then there are people who are specialized in one smaller amount or group of work, which just focus in, for instance, on designing the structure of the vehicle after the big picture people come out with a configuration that needs to be designed in more detail. So there are places for both sorts of people.
So for your students, what kind of recommendations do you give to them to be put in a good position to actually get hired by one of these companies after college? So I imagine internships are probably something that you always recommend, but are there like societies, clubs that they could be part of?
Any kind of outside experience, from rockets to UAVs to airplanes to race cars to whatever it is. If it is engineering related, go for it. If you like to tinker with a car, that's great. If you like to build model airplanes, that's great.
This doesn't have to be confined to the realm of what we normally think of as aerospace engineering then?
No, it's
Okay.
it's more important to have, to most employers that I've talked to, is they want students who have hands-on experience, either working in the field or working in something that is related to that field. So, for instance, I spent many, many years doing model airplanes and rockets before I entered engineering. And so I was able to see as I was taking my classes, oh, that's why they do this, and oh, that's why they do that. And having it reinforced in hardware and hands-on experience is something that you don't get from a textbook.
Yeah. So if you're looking for what affects jobs in engineering, how quickly you're hired and that kind of thing, one of the first things that probably is universal is grades.
Unfortunately.
The better your grades are, the more opportunity you have, and the higher the starting pay you're going to get. Now, grades are overrated, and I haven't seen a really strong tie between top GPAs and top performance.
Exactly.
I see top performance coming from all GPAs, usually. However, that will probably be the major indicator of how quickly you get hired and what you're paid. Number two, if you get any internship, any engineering internship is good experience. I'm a little different than most folks, so I also value any kind of employment.
Yes.
Because employment shows a person knows how to show up on time and knows how to do the job. Although I don't think all managers value that as highly as I do, but any engineering experience will make a difference. And if you get an experience in the niche that you want to work, then that's even better. So it's like good and better. Then your clubs have an opportunity, like if you're working the SAE car, or if you're working the solar boat, or the human-powered vehicle, or the Umbra, which is our rocket club on campus, or one of these clubs, and you go and compete like many of our teams. Don's leading teams that are winning these competitions, first, second, third places, almost every year. You get involved in this, and this can fire the imagination of an employer that will give you the job, even if your GPA is not so high.
Because they realize that you've spent more time building hardware than you have in your classwork.
And you're doing real engineering,
that's
you can close.
That is valued.
I'd also imagine they value the fact that you're actually working with other engineers as well, right? Or
Exactly.
Yeah.
Because they're really wanting somebody that can also play on a team.
Yeah.
The problem with that, or the risk is, it's really easy. I have a number of students with really, really low GPAs because they got involved in these clubs, and then they end up pouring so much time in it. They make that club successful, but their grades tank. And so while the one activity enhances their opportunity, the other one closes their opportunity. And the problem is GPA can have the effect that the managers don't even see you. Because a lot of times you'll be screened out if your GPA is too low by human resources, so the manager doesn't even see what you can do.
And
so you've got to manage how many clubs you're involved in and how your grades are performing if you really want to maximize your opportunity.
But this is a place where networking is really important, because if you know someone within a company, you can hand them the resume and say, look, this student has a lower than regular GPA, but they've done all this work in cars and rockets and planes, and you really ought to consider hiring this person.
Is there like a magical GPA that you could, obviously you want your students to try to get the highest they can, but is a typical cutoff, say 3.0, or what's a...
I've seen 3.0, I've seen 2.7. It just depends on whatever company it is. But if you have a personal contact in that company, you can bypass it.
Yeah, if you want top pay and top opportunity, you need to be up at probably 3.7 or above. However, I usually quote to students like a 3.0. That shows you can do the work, especially if you're involved. If you're down below a 3.0, that means you really haven't ever held the line even at B average. This can make them think you're not sharp enough to get through. That's actually not true, because if you make it into engineering, you're pretty much sharp enough, but it means you haven't prioritized well enough to really perform at an acceptable level in my mind.
But,
so as the further you get below 3.0, the more it's going to probably constrict your opportunity.
but I would say that Cal Poly has a reputation, even with a 3.0, that you're a decent student. And we have a lot of students get hired, even with 3.0.
Okay, so it'll be school dependent sometimes
Yeah,
as well.
there is some reputation, yeah.
I completely agree with that, and with everything else you said. Our department, led by Dr. Mahdi and Dr. Edberg and others, is really well, and so are many of the other departments here at Cal Poly, are really tied in with industry. We have industry action councils that we work closely with. They're on campus. They value our students. And these opportunities give a student who maybe doesn't have as stellar of a resume to get opportunity and get hired. However, if we're talking about what's going to maximize your chances, I would make sure you keep your GPA up, number one. and get internships if you can, number 2, and be as involved in clubs. But if you're involved in clubs, you probably need to take fewer units. The reason students are tanking as they go through this is they try to do all this stuff and they're taking 18 units. That's too many. If you're involved in clubs, you probably need to cut down to a 12 or maybe a 14 units. Take a little bit longer to go through and do well in everything you do rather than doing well in some things and failing in other things and having to come back and play catch up. That's my recommendation.
So nowadays, how much could a typical fresh out of college student who has a degree in aerospace engineering, how much could they be expected to make? What's a typical range of salaries? And of course, it's going to depend on if you're willing to work 60 plus hours maybe versus a 40 hours. So what's a sort of typical range that people could be looking at?
Well, given that this podcast may be listened to
2019,
in the future, this is 2019, I would say a number in the door of about 65 to 70,000 for graduating bachelor in aerospace engineering.
Yeah, so back in 2012, when I was hiring a lot of folks all through the deal, I was seeing 60,000 to 65 with an occasional 70,000 salary going out to a really qualified student. I think that's climbed. I think the number Don quoted is good. It might be a little higher for students that are performing near the top. It might be up closer to 70-ish K for the average. I'm not completely sure.
Again, it depends on the company and the location, but
It does that.
but
Yep.
roughly these numbers.
We're talking Southern California salaries, right? You go somewhere else, that's going to be different.
It'll be a little less, but it's actually more of an advantage because everywhere else is less expensive to live than around here.
True.
In aerospace engineering, how important is professional licensure? So a lot of students, as they get toward the end of their bachelor's degree, they might be debating whether or not they should bother taking the FE exam. And that's the first step that you need to take on your way to becoming professionally licensed. Is that something is that important in aerospace?
So the place where that's most important is civil.
Yeah.
Civil is going to require licensing at most companies. Aerospace, they kind of almost scoff at that a little bit because you don't use it for anything if you're working in aerospace. You're doing everything to FAA requirements. They have a completely different system of DERs that accept the design. DERs and structures and electrical, all these different areas. A DER will go and look at the design and approve it. Look at repairs and approve it.
A DER representing designated engineering representative.
Yep, for delegated, not working for the FAA, but delegated by the FAA.
The other thing is, the other thing is the FE exam does not have anything specific to aerospace. It has mechanical stuff, but not necessarily aerospace.
So
and Todd and I are almost opposites here because I do not have a professional license, and Todd has several.
Yeah, so I do have the PE, and I'm also a DER. But so with that said about aerospace engineering not requiring it, when I finished and started asking around these same questions, why would you not, as a new engineering graduate, get every credential that you possibly can get that says you're qualified to do your job? So I highly recommend going and getting the fundamentals of engineering exam. This is actually, in my opinion, that exam is a little harder than the PE exam because it's broader. You're going to have to perform across a broad length of topics. Once you get to the PE exam, it's much tighter into your niche, and often you can choose the types of problems, or at least you used to be able to choose the types of problems from a larger set of problems. So I highly recommend getting it. Your PE license, which basically says that means you're going to be paying the state every couple years to keep your license active. But basically it says not only do I have a BS in engineering, I also have a license that says the state of California has licensed me as an engineer. I highly recommend that.
Nowadays, how important is it for someone in aerospace engineering to get a graduate degree? So what kind of doors does that open, having a master's, and what other doors are open by having a PhD?
I would say it has become almost a necessity to get a master's degree. It allows you to become more specialized in whatever discipline your degree is in, and hopefully that's something that you're excited about and interested in. And it will increase your salary, and it will increase your status within the company. So many people will graduate with a BS and go to work and then do a master's degree part-time while they're working full-time in order to get it done without reducing their income. And that is something I recommend to most students.
Would you recommend them first getting that industry experience or going straight to get an advanced degree, or is that going to be very student dependent?
I was going to say it depends on what your personal situation is. Some people would rather spend full-time a year or two getting their master's, and if they have the finances to do that, that's great. A lot of people don't, and so they will do it while they're working. And I would say most aerospace companies have an educational program where they will cover much, if not all, of the costs of getting an advanced degree, and they'll pay you more after you get it. So it's a win-win situation.
So I have a really similar opinion. I would agree that getting a master's or a PhD is more important than ever. And the reason is we're really in a global market. We're in, it used to be the United States. If you worked here, you were kind of a little bit in a bubble. We're kind of an international country, but you were competing with United States people. We now have people coming from all over the world, and most of them are highly educated. Other countries recognize the value of education, I think, more than Americans understand the value of education. That's so true. If you want to compete in the international market, you need to have a higher degree. I think a master's is essential or nearly essential. That doesn't mean you can't be a great engineer without it, but I believe to compete well, you're going to want to get that. I think a PhD is for some people and not all people. If you want to go to academia, it's pretty much a requirement anymore. I have also found, curiously, it's funny, when I was a young engineer and I was finishing my master's, I asked a number of managers at Boeing, which was McDonnell Douglas at that time, a commercial aircraft company, whether I should go for a PhD. And nearly unanimously, they discouraged me from doing that. And the reason is they saw it as being overqualified and overthinking and no longer doing practical engineering.
Over-specialized, just very focused on a small
because they had a bad experience working with PhDs who were too focused and couldn't close on anything. Later, when I went into the rocket side, I found the whole perspective toward PhDs was different, and they were respected more than they had been at the commercial aircraft company. I believe the whole industry has changed and PhDs are more respected than they were, but you're going to tend to get more respect and pay and opportunity with a PhD at like a rocket company or a high research company than you will at like a commercial aircraft where you're turning the crank of things that have been done. Curiously, when I finished my PhD, not only did I find more opportunity in academia, which I expected, I also found a number of director engineering jobs opened up to me. A number of companies looked at me specifically because I both had experience and I had a PhD. Folks that were trying to be on the cutting edge of the field, and not all of them were actually doing research. But that made me a front runner in a bunch of job searches. So I think there's a lot of benefit for that. To your question about whether or not to do it, to continue through school versus working, I personally prefer, while this is highly student dependent, if you want to go into academia, probably get all the way through, get your PhD as soon as you can, go and apply, because industry experience in most academic jobs is not going to help you much. In fact, it might be an inhibitor to getting hired. But if you want to go into anything else, I recommend get your bachelor's, start making some money, and go part-time. Many of your employers will actually pay or help pay for your master's, and you'll find that knowledge sits on a better foundation when you're applying some part of your engineering. So I highly recommend most students get your job, start making money, pay back to society, and continue on for your master's or even a PhD. And a lot of folks will see that experience that you have, and your master's will stand on a better foundation. One other comment in terms of pay. So it's true that a master's can tend to expect a higher starting pay than a bachelor's, and a PhD for some jobs will also see a higher starting pay. However, once you're in industry, you go back and you get your master's, it's not necessarily going to mean a bump. It didn't mean a bump in pay for me, and it didn't mean a bump in pay for most of the people that I know. What it does do is if you do go looking for another job, it opens up more opportunity, and those opportunities will tend to have more license to pay you more if they want to. That's what it does for your pay.
So before I let you both go, I'd like to give you an opportunity to give your, let's say, a 1 or 2 minute pitch of why someone who's maybe considering to be an engineer, maybe they're in high school right now, why should they consider aerospace engineering?
I would say that the field of aerospace engineering is very vibrant and changing all the time. And problems that are being solved now were not even anticipated 20 or 30 years ago. And that's going to continue. And to me, having a job is being excited about working on stuff. So as the discipline changes and gets newer and more advanced and so on, there's always new opportunities. So instead of just designing a building or a highway that's pretty much the same 20 or 30 years later, our field is very different 20 or 30 years later. So you're never going to get bored working on projects in aerospace. And that's one of the reasons I like it.
Sure, that's good. For me, I'd say your first thing to consider is, are you good at math? Math and physics, the applied physics. If you're fairly good at those subjects, I would consider engineering as a whole as a potential field for you. Rather than like mathematics or other fields or physics, which tend to be very theoretical but have fewer opportunities. So if you want to go into academia, those are good fields. Or if you have a specific job in mind in mathematics or physics, great. But if you want to have a job, you want some kind of applied science like engineering. Having chosen engineering, the reason I would say come to aerospace is if you really want to do aircraft or rockets or satellites or UAVs or missiles or something like that. Otherwise, I would say consider like a mechanical engineering or a civil engineering, or if you like electricity, maybe electrical engineering, or if you kind of want a little bit of engineering, but you don't really want hard, heavy academics, maybe more like an industrial engineering or an engineering technology kind of job, which will have you on the fringes doing more hands-on thing. And then you want to decide, do you want to do more academic work? Or do you want to do more hands-on work? If you want to do more hands-on, come to a Cal Poly, like Cal Poly SLO, Cal Poly Pomona, or MIT, or something like that. If you want to do more academic work or like research, then maybe like a UCLA or one of those schools that's focused a little more on research. Their teachers will probably be less focused on teaching you and more focused on their research, but it will open the door into that research. If you want to learn and apply, the Cal State system is a great system, and the Cal Poly Pomona Polytechnic School, which has the hands-on focus, will get you more hands-on opportunity. And that's valued by a lot of industry.
Yeah, we've had actually a lot of our graduates in aerospace engineering find themselves interested in controls or electronics, and so they will end up going into a master's degree in, for example, electrical engineering or computer engineering or something like that. And that combination works really well in our industry as well, because many of our engineers are more hardware type people than software type people. And of course, there's a need for both.
Yep, that's true.
Todd and Don, thank you so much for your time. This has really been a pleasure.
Thank you.
Thank you. It's been fun.
I would like to again thank Dr. Don Edberg and Dr. Todd Coburn for spending some time with me to share their lifetime of experiences in the field of aerospace engineering. I hope you now have a much better idea of what aerospace engineers do for a living and what to expect if you pursue aerospace engineering in college and as a career. I also would like to thank Gerardo Maldonado for helping run the soundboard during the recording of this episode. Gerardo is also helping me find ways to improve the audio quality of the podcast, so hopefully future episodes will sound even better. If you enjoyed this podcast, there are a few ways to support it. You can subscribe to the podcast using your favorite podcast app, such as Apple Podcasts, Stitcher, Google Play Music, Spotify, and many others. You can rate the podcast and leave comments on whatever app you use to listen to the podcast. And finally, you can help spread the word about the podcast by telling your friends, family, classmates, or whoever you think might benefit from this podcast. If you have any comments about this episode, feel free to email me at tesepodcast@gmail.com, and I'll place the email address in the show notes. I'll personally read each email and try my best to respond to all of them. Goodbye for now.